Hello, it's John Black, super chemist. We're going to talk about the real truth about time dilation and a black hole and falling into a black hole. And then we're going to go into a woke physics podcaster, and we're going to say, show why he's talking double speak, okay? First, let's talk about one example. We're not doing any orbiting or anything like that, okay? Orbiting makes you go fast. You're going to be time dilated. No, we're trying to get time dilation because of gravity, right? So, and they always say if you park, like this guy right here, if he parks next to a black hole, that he will get time dilated. But see, what they're not telling you is that to park there, to stand there still, you would have to accelerate, right? Otherwise, the spaceship will fall down into the black hole, right? Right? So to park there, you literally have to accelerate, because we all know that if you're in curved space-time, it's a law, a physics law, you have to be accelerating to be standing still relative to the rest of the universe and the planet or black hole that you're falling into. You have to accelerate. Otherwise, we know if you don't, what happens? You fall, right? So you have to be accelerating. So let's say we do what the physicists, Einstein says, you park there and you'll get time dilation. Yeah, this is how you park there, though. You accelerate relative to space-time. And we know that the ship would be accelerating because everything would fall to the bottom of the floor, right? Everything would accelerate to the floor. The floor would accelerate up and everything would be stuck on the floor, right? So we know they're accelerating, even though they're not moving. They're still staying 1,000 miles away or 100 miles away or whatever from the black hole or the planet, right? But we know they got their rockets on and they're accelerating. They're in an accelerated frame of reference. So yeah, they get time dilation, right? Why? Because they're accelerating. That's the only way you can get time dilation. There's literally only one way, is through acceleration. You can say, well, what about high velocity? Yeah, but how do you get there? You can only get there by accelerating to that high velocity, or higher velocity. You can't, or higher speed. You can't have dilation. That's it. You cannot have time dilation without acceleration. You cannot. It's not possible. Not because the acceleration causes the time dilation. It causes you to be at a different speed, and that causes the time dilation, okay? So acceleration is kind of like a boost into another frame of reference, say, where your clocks tick slower, you know what I mean? And you can accelerate more and boost into another, frame of reference where you're even going faster, you know what I mean? And time is moving slower even then. So so time dilation does happen, you know what I mean? If this guy was out here, right, he would experience less time dilation, right? Because the geodesic, see, it's not even got anything to do with physics. It has to do with math. If you have two geodesic lines, right, in curved space, and they are parallel to each other, they will accelerate towards one another, right, and converge and intersect. And over here you can see the acceleration, right? Look. I split it up, you know what I mean? So these sides are even, the angles are even. And I put 3 hours. Here's 1, 2, 3. So you can see the first hour it only accelerated that much. That much. Here, that much. The third hour, look, it's really moving, accelerating towards the other path, right? So this is a mathematical thing here saying that, look, you will be accelerated if these two lines are parallel on geodesics, right? And they are, right? So your paths will accelerate you. So this spaceship over here, it has to overcome this acceleration. See, space-time is accelerating this way, right, towards the black hole. And here, he has to accelerate to overcome that geodesic, right? He has to accelerate the same amount, the the geodesic is accelerating downward, okay? So getting back to the original thing, why does a spaceship out here have to accelerate less to keep it, standing still than this guy? Why does he have to, why is there more gravity here? Why is the acceleration more here? It's just a mathematical thing. It's a graph, you can see right here. If I put you above the Earth, let's say this is the Earth, right, and I put you up here, you can see the acceleration is very small, right? The geodesic hasn't bent that much. But now look at the second arrow. Let's say I put you right above the Earth right here, right? Now look at the acceleration. The acceleration is like big time, boom. And if I put you even further, look, acceleration is even more. That's why, the spaceship here, relative to this point, right? Let's say the Earth was right here. He wouldn't have to accelerate that much because, he would have to accelerate a lot because the geodesic is, the space-time is accelerating down at a faster rate. Over here, let's say the Earth was right here where my hand is, right? And here's the ball. Here, the geodesic isn't accelerating the space-time down that much relative to down here. So you don't have to, so you can just accelerate a little bit here compared to here, and you stand still relative to the Earth, you just float. So the man in the spaceship, he keeps an accelerated frame of reference, right? So he's accelerating the entire time. If you could attach a pull to this black hole, right? Let's say this was Earth. You can attach the pull to it and stretch the pull out all the way out to here and put a clock on it. And then this guy is in a spaceship. He's accelerating, and you put a clock in there. Both of them will be time dilated at the exact same rate. Okay, because they're in the same frame of reference now. That's how you get the time dilation. You have to be in the same frame of reference as the black hole or the planet by being attached to it, touching it, right? Or you have to simulate it, like this spaceship is doing. A clock, you could have a pull coming out here, and a clock will have the same time dilation because it's touching the planet. Okay, you can't do it with this black hole, but you know what I mean. If it was a planet, the ship is just emulating or copying the same exact acceleration that this clock would feel right here. You know what I mean? That's all that's happening, really, basically. So I think we can all understand that, and we can all get that. But it's not some magic gravity field, right? It's not a magic gravity field. The gravity field only affects space-time. Only space-time accelerates down. Okay. Mass bends space-time and curves it down towards the Earth. All the spaceship is doing is, if he lets go of his rockets, is he's just falling in a straight line, constant speed, down to the planet. It's just that space-time is curved. That's it. He's like on a hill, you know what I mean? Just like this green buggy. He's on curved space. Not space-time, on curved space. He's going to fall down that hill. The only way he can stand still is by accelerating up, having rockets right here, right? 10 rockets going at the same acceleration as the geodesic is accelerating down to the Earth. And then he will be standing still on curved space, just like this guy. He's got to accelerate to overcome, the geodesic accelerating in the opposite direction, just to stand still relative to everyone in the world. Because if he puts his rockets on, just like this guy, and it's exactly the same as the gravity, right? He won't roll down the hill, because in curved space you roll down the hill, just like on curved space-time you roll down the geodesic. What is so hard to understand? That part is easy. We can see why the guy gets time dilated and that. So what would happen if this guy, he's floating, above the black hole to stay in his same spot, you know what I mean? The further away he goes, the less he has to accelerate. But if he gets pulled in by the black hole and he can't, you know what I mean? So he starts accelerating more and more and more, trying to overcome it, right? The closer he gets to just like on the geodesic, right? The closer you get, the more you accelerate, right? You can see over here, the more you accelerate, right? So why, think about it now, why does the time dilation happen with this guy? The more he accelerates to overcome this geodesic, the more, the faster he accelerates, the more he gets time dilated. Yeah, because the more you accelerate, the acceleration is doing it. That's what's dilating you, man. Not the gravity, not the field. The field only, affects space-time itself. Space-time accelerates. You keep your same spatial coordinates relative to space-time, so you stay inertial. Okay. The only way that you can get the, if you're falling, the only way you can get the time dilation is to simulate that same acceleration you would get if you were attached to the planet or the black hole. And how do you do that? You accelerate. You turn your rockets on and you accelerate the same exact opposite acceleration that you would get over here, you know what I mean, from your geodesic. That's simple. And what would happen is you'd start going so fast, okay, this wouldn't happen because you'd run out of rocket fuel, okay, so it wouldn't happen. But let's say it did. You kept going and going and going, and you're going faster, 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 faster. At some point, you're going to be so close to the speed of light, right? You've accelerated to the speed of light, man, that you have to be almost going at the speed of light to stay still relative to the rest of the universe and to the black hole, right? You have been time dilated so much that like 1 second to the rest of the universe is like, 1 second to you in the ship, in the ship accelerating, right? 1 second to you will be like 1 billion years to me outside watching you. You know what I mean? Your time has slowed down almost to zero. Okay, they say that you float to the, to the surface and then you stop and you just stay there forever. Bull. You don't stay there forever because that would mean that time stopped, and time never stopped for you. Okay, it just slows down so that trillions of years it goes by before 1 second goes by. For you, because you're accelerating so fast. Not because you're close to the black hole and there's a gravity field that's affecting you. Yeah, it's affecting space-time, which is affecting you because now you have to put on your thrusters. You have to accelerate. It's the acceleration, though, that makes you time dilate. Okay, it's nothing else. It's not the curvature. It's not traveling constants. Because if you let go of the rockets and you just free fall, you're just going at a constant speed in a straight line. You're being inertial. The only way you can change that, you got to turn your rockets on, man. You turn your rockets on. Now when you're in an accelerated frame of reference, you're making your speed higher and higher and higher, and each level of speed that you get to makes your clocks tick less and less and less. It's not just that this guy here floating and he's floating, so his clocks tick different? No. Why would his clocks tick different? He is not accelerating. He's standing still relative to space-time. Only this guy is accelerating. The guy with the rockets on is accelerating, and the guy who doesn't have rockets on him and everything floats. Yeah, I know it's hard to believe, but that guy who's floating and has no rockets, he's not accelerating. I know it's weird. I am crazy, I guess. And the guy who has rockets on accelerating, I'm saying he's accelerating. Because he's accelerating relative to space-time. To the rest of the universe and to this black hole, he's standing still. Because you have to accelerate in curved space-time to stand still. Otherwise, you fall down to something. He's a planet, a black hole, something. You fall to something. That's what curved space-time is. You're near something massive, and he's pulling you down, right? But it's only accelerating space-time, okay? And that's what matters when it comes to acceleration. Like, not the fact, because you're still accelerating. In all these examples, you're still accelerating, right? But you're not in an accelerated frame of reference because you're not actually being accelerated. Just your paths are being accelerated. You know what I mean? That's the thing that these people don't seem to understand. These woke physicists, podcasters, they don't seem to understand that just because two paths are accelerating, right, towards one another, It doesn't mean the objects are accelerating. You know, yes, they're accelerating towards one another, but are they being accelerated by any force? If not, then they're still in an inertial frame. What's so hard